Hi guys, welcome to Let's Get to the Marks. I got a bit of a cold, so red nose and voice is a bit funny. We're looking at nucleophilic substitution of halogenoalkanes, and this is an important part of A-level chemistry. Okay, what is a halogenoalkane? Let's start with that. Well, we can also call them haloalkanes, not just halogenoalkanes. And a haloalkane, something like ethane, where one of the hydrogens has been swapped for a halogen. So today I'm going to be looking at chloroethane as my halogenoalkane, but it will be the reactions are the same no matter what your halo or halogenoalkane is. So we're going to be looking at nucleophilic substitution. Now, it's not just halogenoalkanes that undergo nucleophilic substitution, but mainly at A level, you will be dealing with halogenoalkanes. Why do they undergo nucleophilic substitution? Well, if we look at this part, of the carbon-chlorine bond of a halogenoalkane, you can probably guess straight away what's going to happen. The carbon is not very electronegative, but the chlorine is. So this difference in electronegativity pulls the electrons over close to, this isn't a playing ball, it pulls the electrons closer to the chlorine in the covalent bond. What does this do? Well, this makes the chlorine delta negative, which is slightly more negative than normal. The electrons at any one time in that bond are closer to the chlorine. So it hasn't actually got a full negative charge, but it's slightly more negative than normal. And the carbon becomes delta positive, slightly more positive than normal. And what this does is this opens up this carbon atom here to nucleophilic attack, because the word nucleophile, nucleo means nucleus, and what a nucleus is, or nuclei like, well, they're very positive. They contain lots of protons. They don't have any electrons, protons and neutrons, so they have a positive charge. And phile means love. So nucleophiles, which are the reagents we're going to be looking at that attack halogenoalkanes, love positive charge. So this is a polar bond that we find on halogenoalkanes, and this opens up and makes halogenoalkanes susceptible to attack from a species or a group of substances called nucleophiles, which love positive charge. So let's get into this. Here is my lovely chloroethane. And what it has to watch out for is that there's 4 substances or nucleophiles that are looking to attack it. And we have hydroxide ions, which you guys have all heard of before. And we have cyanide ions, and they have a minus charge as well. And we have ammonia. So in A-level chemistry for AQA and other exam boards, you will need to know about the reactions where these 3 nucleophiles attack, by nucleophilic attack, any halogenoalkane or haloalkane. So let's have a look at how the hydroxide ions attack this bond. So first of all, I'm going to highlight that the chlorine is slightly negative. And then I'm going to highlight that my carbon is slightly positive. And along comes my hydroxide ion. And oxygen in this form has a lone pair of electrons. And essentially what goes on here with nucleophilic attack is we get a dative covalent bond, or a coordinate bond, as you've probably heard of before. So what happens is this pair of electrons going to attack this positive carbon. And we're going to form a bond there between the hydroxide ion and the carbon. Now, if you can remember, what group of the periodic table is carbon in? You should remember carbon's in group 4. So how many valence or available electrons does it have for bonding? The maximum amount of bonds that a carbon atom can normally have is 4. So we're going to form a fifth bond here. And this is the carbon atom is going to want to stabilize itself. And it does this by chucking out the chlorine. And it will do that by sending the pair of electrons from this bond to the chlorine atom. And the chlorine atom is going to break off and do its own thing. So our chlorine has broken off. Now, the hydroxide, it's very important with these curly arrows. You see, I've just drawn this curly arrow right here. It's really important that you show that the pair of electrons is going to this chlorine atom, and you must touch the bond here. Whatever you do, you mustn't do that and think you're going to get a mark in the exam. You will not. That looks like the pair of electrons that's coming from the positive carbon atom. Well, that's not going to happen. So we must show that the pair of electrons is coming from the bond and going into the chlorine atom. We also put a double-headed arrow on the end of that, and the double-headed arrow, this part, represents 2 electrons. There's other parts of chemistry where you use a single-headed arrow, and that represents a single electron. We're not going to look at that now, as we're just looking at double headers at the moment. So what does this produce? Well, this produces ethanol. And it would be any other alcohol. It could be propanol if I had chloropropane, or if I had bromobutane, I would produce butanol. So you produce the alcohol in relation to what haloalkane you're using. Now, what happens to this chloride ion? Well, this depends in where I got my hydroxide ions from. So if my hydroxide ions came from potassium hydroxide solution, then I'm likely to form potassium chloride as a side product. If I got my hydroxide ions from a sodium hydroxide solution, then I'm going to make table salt, sodium chloride, which is likely to join with the chloride ion. So that's the simplest nucleophilic attack that we have. Let's get on and look at the more complicated ones. So we can also do nucleophilic substitution with ethanolic cyanide. Now, this is a cyanide ion, and the cyanide ion is made up of a carbon and a nitrogen. Now, what we have here is the word ethanolic cyanide, and this just means that cyanide is dissolved in ethanol. So that means dissolved in ethanol. So again, negative, positive. Think about it. Where is my lone pair going to attack? Will it want to attack the chloride? No, the chloride has a slightly negative charge. This will repel the lone pair. So instead, the lone pair decides to attack here. Now, what does that cause the carbon there to do? Well, it can't have 5 bonds. It's got to lose a bond. So it decides to lose this bond here and send 2 electrons there, leaving our chloride ion on its little lonesome, which now has gained that pair of electrons. And quickly redraw this. There is another question that students sometimes ask here with my incredibly bad D in GCSE art skills. So what we have here is we've extended the carbon chain. You can see there's now 3 carbons here. So what do we call this? It's no longer a 2-carbon molecule. It's no longer eth. It's now prop. So we actually call this propane nitrile. And in A-level chemistry, that's how you name it. You name all 3 carbons. There are other situations where you could call this ethyl, say that's an ethyl group. And we could call this sort of ethyl cyanide or something else. But we are calling it in A-level chemistry propan or propane nitrile. Now, again, what happens to our chloride ion? Well, it depends. What if the cyanide was KCN, then we're going to have some potassium ions floating about, and we might get potassium chloride again. So it purely depends where we got our cyanide ions from. Also notice the conditions. It says reflux. So my conditions are ethanol and reflux. Hold on a minute. Yeah. There we go. Ethanol and reflux are my conditions. We make propan-nitrile. Now, some students do ask me over here, sometimes they say, sir, how come when the carbon decides to break off the chlorine atom, why doesn't it just break off this instead? Why does it have to get rid of the chlorine? Why can't it just kick out one of the other hydrogens? Well, plenty of reasons for that. Obviously, chlorine is more electronegative, so the electrons are closer to the chlorine, making it easier for that to leave with the lone pair. And also, the carbon-chlorine atom, or the carbon-chlorine bond, has a lower bond enthalpy than a carbon-hydrogen bond. There's like 50 or maybe 70 kilojoules difference. So it's always easier energetically for it to get rid of the chlorine atom there. Okay, so we've now dealt with the first two. Now it's going to get tricky. We're going to look at the third nucleophile, and this is the one where people get quite baffled. So the third nucleophile we have down here is ammonia. Now, ammonia has a lone pair. We don't need to write a negative charge. It does not have a negative charge, but it has a lone pair. And we have delta negative and delta positive. So slightly negative, slightly positive. So same procedure as normal for the first step. So normally, if you get a nucleophilic substitution question, they're normally 5 marks. So you're looking at 5 marks, quite a healthy lump of your exam. And the first couple of marks are literally going to be scored from, are you drawing this arrow from the lone pair to the positive carbon? Whatever you do, don't get sloppy. I've seen people do this and lose the marks, just casually putting that lone pair into a bond. Now, why would the lone pair attack a bond? The bond is a pair of electrons. A lone pair is going to be repelled by a pair of electrons. So do not be sloppy with your arrows. Forgive me if I am. I'm allowed to. Right. There we go. And so same procedure as normal. We've got the electrons coming out of the chlorine bond and going into the chlorine atom, both the pair, and we have a pair of electrons joining here. Now, this is where it gets different than the other ones. So we're now going to draw the intermediate stage. Whereas with the others, we don't have this. It would be nice if I stayed with the lovely green color, wouldn't it? In fact, let's do that. Let's get rid of this. And let's zing back and use the green. There is a reason why I put that in green, and that will become apparent in a little bit. I've never seen such a badly drawn molecule. Okay, let's rearrange this. Go black, please. No, black. Yes. Here is our lovely ammonia molecule in all its full glory. Anyone spot a problem? The problem is that when nitrogen is bonded, when it has 4 bonds, it becomes an ammonium ion. So this is an ammonium ion, and it's a cation. So it has a positive charge there. Just like if you remember NH4+, your ammonium ion, well, guess what? I guess this is a ethyl ammonium cation. So you probably will never, ever have to name that, but that's what that is. So we don't end here. There is another step. And what happens is a second ammonia molecule. So normally this is excess ammonia. So we have lots of ammonia hanging about. A second ammonia molecule says, hello, comes along, Now, ammonia is quite happy to form NH4. So what this lone pair of electrons, and this is probably the biggest mistake that students make in this mechanism, students will normally draw this arrow to here or to the bond itself. Don't do that. It actually attacks the hydrogen here and forms a bond with the hydrogen. Another mistake students do, very common mistake in this mechanism, is they go, okay, I remember it's going to form NH4. I'll draw the hydrogen joining to the ammonia. What you're saying there is not going to happen. So the hydrogen is not going to go and move there. It's the electrons that move. The lone pair moves. Things don't move towards the lone pair. So lone pair moving in. What's going to happen here is we are going to get our amine forming. And this molecule is called an amine. When you have NH2 here, we have ethyl amine. So lovely. That wasn't the worst thing in the world. So that wasn't the end of the world. That wasn't the worst thing in the world, the formation of ethyl amine. And we can write an overall reaction for this. So we can write it like this. CH3, CH2, Cl. We got 2 ammonia molecules involved, as we had one here and one here. So 2 ammonia molecules involved. And that makes, oh my good gosh, ethylamine. I'm running out of room. When you get to the edge of the screen, it gets all a bit messy. So we've got ethylamine there. And what happens to our, which we didn't show, what would have happened to our chloride ion, and you can work this out. Okay, let's do the lone pair there. Right, what's going to happen to our chloride ion? Well, remember we had ammonia forming here. Our chloride ion and our ammonia are going to get together and form ammonium chloride, which is going to be NH4Cl. We just about squeezed that in. So ethyl chloroethane reacts with 2 ammonia molecules, forms ethylamine and ammonium chloride. I'd love to say we're stopped there, but actually it gets more complicated. And this is the bit which gets really hard. So ethylamine still has a lone pair, as nitrogen, when it has 3 bonds around it, will have a lone pair always. This means that our ethylamine here can become a nucleophile itself. Ethylamine is a primary amine. There are 2 hydrogens available on the nitrogen. We call that a primary amine, or there's one R group. It has one R group attached. This is the R group. And when there's one R group attached, we call this a primary amine. And that little sign there, shorthand for primary amine. Right, let's have a look. Here's our primary amine down here. Here's our ethyl amine. And our ethyl amine is now going to come to another chloroethane, another halogenoalkane, and it's going to go and attack that carbon atom. And we're going to get the very familiar by now curly arrow with our electrons going there. And then what we're going to have, and this is where it starts to get messy. So you can see why I've drawn them in different colors now, because we're going to add them on. So let's just do CH3, CH2. Excusez-moi. And then we're going to have, and where's the green? Okay, so now you can see Oh, I've just seen a really horrible mistake. Can anybody see my mistake in drawing these? If we go over here, it's not really a mistake. It was a purposeful thing. And I've done it with, I'll close in on the pink one in a sec. Look how I draw this now. So your carbon atom, it's quite awkward when you draw things on the left of a molecule and you want to attach an R group, like an ethyl group. Your carbon must be the thing that's attached. They will actually take the mark off for the way I did it there. And you can see here again, we've got the same thing going on here. It always feels nicer to do it like that, but you have to show that that bond is bonding to the carbon. You mustn't show that it's bonding to the hydrogen. A hydrogen can't possibly have two bonds, so you're making a big mistake if you do that. So it looks really ugly, but that's how you draw the ethyl group when it's coming off of the left of a molecule. Okay, so let's have a look. What have we got here? We have two hydrogens. Guess what's happened? We form an ammonium ion again. This time, this would be called diethyl ammonium cation, but you don't need to know the name of that. So what's going to happen here to stabilize this? Same as before, we're going to have an NH3 come attack here, and this bond is going to break and its electrons go here. Which did we even show over here? I don't think we actually showed that here. So this bond breaks and goes there. So I didn't actually show that the electrons from that bond, in my rush, I forgot to show you, the electrons from this bond go here, and the same thing each time. So the electrons from here are going here, and we're going to get the next horrific product, which is going to be diethylamine. And diethylamine is this NH, this little group here is going to form NH4 plus, and this is going to join with our pink chloride ion, and we're going to get, yikes, we're going to get ammonium, yikes, chloride like that. So yeah, and then we're going to have diethylamine. Okay, over here now, this keeps going and we keep going. This, by the way, if I flick back, diethylamine diethylamine, how many R groups are attached? Well, we've got R1 and we've got R2. So this is a secondary amine because there's two R groups attached to the nitrogen. So we'd actually call that a secondary amine. Guess what? It can make a tertiary amine. And let's get into it with the orange chloroethane to show the next line. You can see I've already done the arrows for you. So the arrows, the lone pair goes here. This bond breaks. Both the electrons go to the chlorine, forming the chloride ion at the top here. The orange ethyl group has now joined on here. We've got the pink one, which was the second one to join on, and we have the first ethyl group there. So we've now got triethyl, well, down here, triethylamine has been formed. And triethylamine, you can count the R groups. We've got, yikes, got R1, R2, R3. This is now known as a tertiary amine, a tertiary amine. And guess what? It's still a nucleophile. There's still a lone pair there. So we're talking about when you use ammonia, excess ammonia, you get multiple products. So we got the ethylamine, the primary amine. We've got diethylamine, the secondary amine. And we've got triethylamine, the tertiary amine. There's one more to form, folks. And also, as another product, we get the ammonium chloride, but that stays the same each time. If I was dealing with chlorobromine, sorry, if I was dealing with bromoethane, I'd be getting ammonium bromide. Or if I was dealing with iodoethane, I'd be getting ammonium iodide. I need to talk about that as well in a second. We're nearly done. We're nearly finished. Here's the final one, guys. So if you've hung on all the way, well done. And I hope this has been of some help to you. Right. That final triethylamine can attack yet again, as it is a nucleophile. Its lone pair can attack this carbon atom. The bond here can break, sending the electrons there, and we can actually form, as you can see here, what do you call 4 ethyl groups? Is it quad? What is it? Well, I hope you know. What do you call it? It's tetra ethyl amine. Remember, this could be methyl, propyl. It just depends how long that side chain is. So this is tetra ethyl amine. And yeah, that is a quaternary, also known as tetraethylamine, quaternary ammonium ion. So can form a quaternary ammonium ion. And guess what can happen here? Notice there's no ammonium ion formed here. There's no ammonium ion coming off here. So what we've got going on here is our chlorine can then, our chlorine here can then react with this, and we can get really, we can actually get a, oh, I can't spell, quaternary, oh, that's definitely not right. Just doesn't look right when I type sometimes. Quaternary ammonium chloride. So we could actually have the chlorine can now bond because that nitrogen is positive. Chlorine can actually bond to that. And yeah, so what would the molecular formula of that look like? Well, there's quite a few ways. Well, I could do it as like a structural formula like that, and I guess I could put a 4 and then a nitrogen and then a chlorine, or I could do, I could show the charges if I want. So I could go plus, Cl minus. That's it really, folks.